today's lecture, we're continuing with Chapter 4 from Lessons 5 to 8. Lesson 5 covers line plots. So the key ideas to keep in mind with this lesson, a line plot is a graph that shows the frequency of data along a number line. And based on frequency tables, line plots consist of a horizontal scale and then points or X's placed over the corresponding numbers. Line plots help us to interpret the distribution of data. So the same kind of information that can be expressed in a frequency table can also be expressed in a line plot. A line plot shows the frequency of data along a number line. One type of question that you may encounter, you may be asked to analyze data on a line plot. Another type of question could ask you to use a frequency table to place an element on a line plot. So in this example, we're told that the Student Health Services Department at a university surveyed several students and asked them how many times they visited the school's gym. The following, or the frequency table showed on the right, shows the results for several students. So we see weekly gym visits in the first column, or in the column on the left. And then on the right, we see a tally for the number of students that show up. The Health Services Department then decided to create a line plot in order to see the distribution of gym visits. So each X represents a student. And so we can see, based on the weekly gym visits, one visit we have 2 students, where we see 3 visits we had 3 students, and so on. So you can see from this line plot that there is an uneven distribution or arrangement of students across the numbers of possible gym visits. 3 visits per week has the highest frequency, as we can see here, with 3 students, meaning that more students go to the gym 3 times per week than any other number of visits. So you can also see the data range extends from 0 visits per week to 7 visits per week. No student visits the gym more often than 7. So the data point showing the student who visits the gym 7 times per week is the outlier. And that just means a data point that is distant from where most of the data is clustered. So the mathematical reasoning test may ask you to identify the highest frequency, range, and outliers, or it may give you some data and ask you to plot or to place X's or dots on a number line to create a line plot. In this example, we're told that students in Ms. Jones's class took a math test, and their scores on the test are displayed on the line plot below. Each dot represents a student, which grade displayed the highest frequency. We can see that more students received a C than any other grade. We can see on the line plot the distribution of dots is 6. Therefore, grade C has the highest frequency of any grade on the plot. The range of grades on the math test was from D. You can see here 3 students received a D, which was the lowest grade, to A. 2 students received an A, which is the highest grade received by any student. So your practice exercises starting on page 776 to 778. Lesson 6 covers histograms. Similar to line plots, histograms display frequencies, but they do so in a very different way. So consider this example. Graham is a veterinarian, and last year he decided to track client appointments for spring shots. The table on the right and the histogram which will follow represent his results. So we can see here on the left, we have the week, and then on the week in question, and then on the right, we have the number of appointments made that week. So for example, the week of March 15th to March 21, Graham saw or had 8 appointments. So the histogram on the right has 2 axes, a vertical axis or the y-axis, okay, representing the number of appointments, and then a horizontal axis, also called the x-axis, and that represents the weeks. And so the area of each bar represents the number of appointments for that week. So not only can you see the number of appointments that were made in any given week, but you can see how the frequency of appointments changed over the weeks in the chart. Histograms can also be used to show percentages. So if we were to change the histogram about Graham's appointments so that each bar represents the percent or the percentage of total appointments each week, it would look something like what's on the right. So going back here for the first week of March, he had a total of 2 appointments. To find the percentage, you would just simply add the total number of appointments here on the right hand side, and that 2, 4, 8, 11, 14, 19, 20. That totals to 81. And then for the first week, he had 2 appointments. So 2 divided by 81 would be around 0.2, which in percentage form would be around 2%. And you can see that reflected here on the percentage version of our histogram. We can see that for the first week of March, percentage of appointments was 2%. Again, if you wanted to find out, let's say, the percentage of appointments he had in the second week of March, you would just divide 4 by 81, and that would be around 0.4, upwards of 0.4, maybe around 0.5, and then you could just change that decimal to its percentage equivalent. You can see here that for the second week of March, the percentage of his total appointments was 5%. Okay. Because the percentages add up to 100, the areas of all the bars add up to 100. So essentially, if you were to take all the areas under each bar, meaning the portions shaded in gray, and you added them all together, they would add up to 100. So in this example, we're being asked what percentage of appointments for spring shots occurred during the first 2 weeks of March. So we just go to our percentage histogram. We know that the first week of March represents around 2% of the total number of appointments. And then the second week of March, we've established represents around 5%. So if we wanted to find out or to answer the question, you would simply just add the first week, the percentage of appointments in the first week, 2%, to the percentage of appointments in the second week, 5%, and our approximation would be around 7% of appointments for spring shots occurred during the first 2 weeks. So here's a test tip. Some multiple choice questions may ask you to identify graphs that represent different types of data collection, and you may be given some data and asked which graph represents that set of data. So work on the practice exercises starting on page 782. to 786. And again, these are the page numbers for the Kindle version. So just be aware of that. The lesson 7 is on probability. And the key ideas brought forward here is that probability is a ratio. It can be expressed as a ratio, fraction, a decimal, or a percentage. And last couple of lessons, we've seen examples of how a ratio can be expressed in fraction form, and then that fraction can be transformed into its decimal equivalent, and from the decimal equivalent, we can find the percentage or the percentage equivalent. Theoretical probability is the ratio of favorable outcomes to possible outcomes. Experimental probability is the ratio of favorable outcomes to the number of trials in an experiment. So simple probability essentially tells us whether something is likely or unlikely to happen. The probability of any event can be expressed by a number from 0 to 1. If an event has a 0 probability, that just tells you that the event is unlikely to happen. And if an event has a probability of 1, know that that means that the event is certain to happen. The probability of the occurrence of most events are somewhere between 0 and 1. So to find the probability of a simple random event, we must identify favorable and possible outcomes. A favorable outcome is the event that we are interested in, and then the possible outcomes are all the possible events that could occur. So theoretical probability is sometimes called simple probability. Theoretical probability is essentially the ratio of favorable outcomes to possible outcomes. So in this example, we're being told that the spinner or a spinner is divided into 8 equal sections. What is the probability of spinning a 4 on the spinner? So we look at our spinner, we see, we count the total number of sections to verify, and we see 4 equal parts on the top and 4 equal parts on the bottom. So our spinner is correctly divided into 8 different parts. And then we're being asked, what is the probability of spinning a 4? And so we look on the spinner, we see that here's one part that is labeled with a 4, and here's another part that's labeled with a 4. And we know, so that's 2 parts total that are labeled with a 4. And we know that the total number of parts or the total number of sections that we have is 8. And so we can use our probability ratio to determine the probability of spinning a 4. And so we would simply write down the number of favorable outcomes. In this case, we're interested in spinning a 4, and we see that, or we've already established that there's 2 parts that are labeled 4. So we write down 2. And then we also know that the total number of possible outcomes is 8. So 2 over 8. We can reduce that to its lowest terms. 2 goes into 2 once, 2 goes into 8 4 times. So we can answer our question that the probability of spinning a 4 on the spinner is 1 out of 4, or a quarter, which can be written in decimal form as 0.25. The percentage equivalent of that is 25%. So in a multiple choice probability problem, skim the answer choices to see if they are in fraction, percentage, or ratio form, because knowing the answer form will help you decide how to approach your calculation, or how to present your final answer once you're done with your calculations. So in example 1, probability was based on what we knew could happen. Another type of probability, as mentioned earlier, is called experimental probability. And experimental probability is based on what actually happens during the different trials of an experiment. So the number of trials are the number of times that you can try your experiment. In this example, we're told that Ricardo and Scott used the same spinner to play a game. They kept track of the numbers that they got on each spin for 20 spins. Those numbers are shown below. So for example, on the first spin, they got 2, and on the last spin as well, the 20th spin, they got 2. So based on the results, what is the experimental probability of spinning a 4? Well, you would simply go back to your list of numbers and you would count the number of times that 4 occurs. So here's 1 4 on the second spin. Here's another one on the third spin. So that's 2 so far. 3, 4, 5. And here we have 6. So we have a total number of 6 4s. And then you would just go back to your probability ratio. The number of favorable outcomes that we're interested in is the number of 4s that they could get, and we've counted and we've seen that that's 6. And we would just simply divide that by the total number of trials in the experiment. And we've established, or the question tells us, that they spun for a total of 20 times. So 6 to 20 is our probability ratio. You could recognize that 6 and 20 are both divisible by 2. So 6 divided by 2 is 3, 20 divided by 2 is 10. And so 3 over 10 is our probability ratio, which can be expressed as 0.3. Equivalent of 3 over 10 is 0.3. Or you can express that in percentage form, which is 30%. Okay. So notice that experimental probability is close to, but not necessarily equal to, theoretical probability. Theoretical probability can tell you what will probably happen, but it can't predict what will actually happen. So in this scenario, we know what actually happened during their experiment. They spun exactly 20 times, and for each spin, they got a different result. So we know exactly what happened, and we can use our probability ratio to find different probabilities based on whatever outcome that we're interested in. So there are practice questions on page 788 to 791 on probability. Do make sure that you attempt those, or on simple and experimental probability, rather. So lesson continues on dependent and independent probability. You know how to find the probability of a single event, and use this knowledge to find the probability of 2 or more events. In this example, Brad tosses 2 quarters in the air. What is the probability that both will land so that the heads sides are showing? So imagine Brad holding 2 quarters in his hands, and we're being asked to find the probability that once he tosses the quarters and they land back in his hands, both quarters will show 2 heads. So one way to solve the problem is to just list or diagram all the possible outcomes. Start by writing down what happens if the first quarter is heads, right? Well, there are 2 possibilities that could occur once he tosses it in the air, right? Quarter 2 could be heads as well, and so then you would have heads and heads, or quarter 2 could be tails. So this diagram is representative of what's going on after the quarters have landed, okay? So imagine he's tossed the quarters in the air, they've landed back in his hands. So what happens if the first quarter, or quarter number 1, is heads? Well, there are 2 possibilities. Quarter number 2 could also be heads, or quarter number 2 could be tails, right? And so we see that reflected here. All right. What happens if the first quarter is tails. First quarter landed back on his hands as tails. Well, there are two possibilities for the second quarter. Quarter number two could be heads as well. So we have tail and a head, or quarter number two could also be tails. And so then we have two tails, right? And so we can see on the right-hand side here that there are four possible outcomes. He could have two heads, he could have a head and a tail, he could have a tail and a head, or he could have two tails, for a total of four possible outcomes. But we're only interested in one, and that's our favorable outcome, which is two heads, right? And so the probability of having both land with heads side up is 1/4, or 25%, as shown in our diagram here. So you can use multiplication to find probability. So if we were to return to our previous example, the probability that one coin will be heads is 1/2, right? It's either heads or tails, either or, right? So there are two total possibilities, heads or tails, but there's only one possibility for heads, so that's 1/2. And the probability that the other will be heads is also the same thing, right? Because equal probability, and right, so then you would just multiply 1/2 by 1/2 to find the probability of both events. And if you remember from our lesson on fractions, when we're multiplying, we multiply across. So 1 times 1 is 1, 2 times 2 is 4. And again, we found the same answer, which is 1/4. So this is just showing you two different approaches to answer the question. Okay, so there's somebody in the waiting room. Hi, Julie. Can you hear me?
Yes, now I can hear you.
Okay, that took a minute to admit you for some reason.
Yeah, I don't know. My computer had to update and everything. I don't know what was going on.
Okay, okay. All right, so two coin tosses, this example, are independent events. Events are independent. One does not affect the probability of another. In example 4 that follows, the events are dependent. So once the first event takes place, the probability of the second event is changed. In this example, we're being told that a box contains 4 blue marbles and 2 red marbles. So if you select 2 marbles from the box, what is the probability that both will be blue? Remember again, we just went from discussing independent events where one doesn't depend on the other. Now we are talking about dependent events, but there's a note here telling you to just imagine that, you know, since you're grabbing both marbles simultaneously or at the same time, imagine that the first marble and the second marble are not independent draws, okay? So even though the marbles in the box are taken out at the same time, think of one as the first marble and the other as the second marble. Again, they're not independent draws. This is a dependent draw, but still just think of them as your first and second marble. So since there are 6 marbles in the box and 4 are blue, the probability that the first marble will also be blue is 4 out of 6, right? Again, going back to our probability ratio, we know that 4 is the number of outcomes that we're interested in. 6 is the total number of possible outcomes. So this reduces to 2/3. We recognize that 2 goes into 4 2 times, 2 goes into 6 3 times. So first probability is 2/3. Then you want to assume the first marble selected is blue. Now there are only 5 marbles in the box and there are 3 are blue, right? So we've selected 1 marble of the 6. That marble happened to be blue. And so now there are only 3 marbles left that are blue and 2 that are red. And so the probability that the second marble is blue is 3/5. Why? Because we only have 3 marbles left out of 5 possible options. So then you would multiply your first probability, which is 2/3, which we found by reducing 4/6, by your second probability, which is 3/5. And again, from our lesson on multiplying fractions, we know that we multiply across. So 2 times 3 is 6, and 3 times 5 is 15, or 2/5. Recognize that 6 and 15 are both divisible by 3. So 3 into 6, excuse me, is 2. 3 into 15 is 5. And so the probability that both marbles will be blue is 2/5. So note that the events in example 4 would not be dependent if the first marble were replaced before the second marble was selected, right? And in this example, it would be an independent event if you first selected one marble, you saw the color, and then you put it back to bring your total back up to 6, total number of marbles, and then you selected another event, you selected another marble. Those would be 2 separate events, right? But in this example, we selected both marbles simultaneously. And so that's why that scenario, it's classified as a dependent event, right? But remember, the note was telling you, even though you're selecting the marbles simultaneously, still think of the marbles as 1 and 2. So even though you have 2 marbles in your hand, it was still one singular action that you needed to draw out both at the same time. So always think carefully about the situation to decide whether 2 events are dependent or independent. Okay, and you can just kind of do the same walkthrough that I just did, right? Is the event happening simultaneously, or is it happening one at a time? If it's one at a time, they're independent. If it's happening simultaneously, they're dependent, meaning both events need to happen at the same time. Both events depend on each other. You need to grab 2 marbles at the same time to meet our definition of dependence, right? So how many marbles do you have in your hand in that first draw? Well, it depends. Did you grab 2 at the same time? Yes, you did. So that's a dependent event. There are practice exercises starting from page 793 to 796. And again, this is the Kindle version of the book. So make sure that you just work on the exercises that follow the lesson in your book, lesson 7 in your book. The final lesson for today is on combinations. The key ideas to keep in mind here is that combinations are used to select several things out of a larger group when the order doesn't matter. So if you were asked to find out how many ways to combine items from one group, we could use an organized list or a table. And if you were asked to find out how many ways to combine one item from each of a number of different types of items, then you could use a tree diagram or the fundamental counting principle. And you'll see what this means in the examples that follow. So combinations with one type of item, sometimes the GED, the mathematical reasoning tests, will ask you how many ways that you can combine a set of items. And sometimes you may have only one type of item to combine, and there are times where you may have more than one type of item, and the difference will determine your problem-solving strategy or your problem-solving approach. So in this example, we're told that Pablo is going shopping at a fruit stand that sells apples, bananas, grapes, and pears. Pablo will buy 2 different kinds of fruit. How many combinations of 2 kinds of fruit can Pablo buy? Well, the question is essentially asking you to list the possible groups of 2 out of the overall set of 4. We're being asked out of these 4 fruits, or out of the set of 4, how many combinations of 2 can Pablo buy, right? So the order in this instance wouldn't matter, because if he bought apples and bananas, that's no different from him buying bananas and apples. Okay, same thing. So to solve this problem, you would just simply make a list, right? Start with the apples and list all the possible combinations that include apples. So he could buy apples and bananas, he could buy apples and grapes, or he could buy apples and pears, right? For a total of 3 combinations with apples. Then you want to make a list of, start with bananas and include the remaining fruits, right? So he could buy bananas and grapes, he could buy bananas and pears. And remember, we're not saying that he can buy bananas and apples, because we've already established that apples and bananas and apples, same thing. And we've already accounted for that combination in our first list, okay? So in the second list, you would just start with the next fruit. You could buy bananas and grapes, or bananas and pears, right? And then you would do the same for the remaining combination, which is simply just grapes and pears left over. There are no remaining groups with pears, because we've gone through, we started our list with apples, we started our list with bananas, we started our list with grapes, but with pears, there's nothing else that would make a combination of 2, right? So we're done with our list. And we can see, based on everything that we've written down, because remember, you're writing down the combinations, that he could buy apples and bananas, apples and grapes, or apples and pears. So this is our list with just apples. He could also buy bananas and grapes, or bananas and pears, or he could buy grapes and pears. So we have a total number of 6 possible combinations, right? And then you could also draw a quick table to include a column for each fruit, as shown on the right-hand side here. And then you would place 2 X's next to each row to represent a combination of the 2 fruits. And notice that there are 6 total rows, which represent the total number of combinations, right? So let's see what's going on with our table here. We see 1x for apples, 1x for bananas to show our first combination where you could buy apples and bananas. We see 1x for apples, 1x under grapes to reflect our second combination where he could buy apples and grapes. We see 1x under apples, 1 under pears for our third combination here, where he could buy apples and pears. Okay, and then we're moving over to our next column here for bananas only, right? So we filled in our first 3 rows already. So we're going to start with row number 4, and we see from our list that the next combination is bananas and grapes. So you place your X here under bananas and an X under grapes. And then what are we going to do next? We're going to go back to our list, and we see that the next combination is bananas and pears. So we have an X under bananas and an X under pears, right? And if you notice, right now we've marked a total number of 5 combinations. So we're in row 5, okay? So we're just going in order. And our final combination is going to go into row 6, right? And our final combination is for grapes and pears. So we go back to our 6th row and we mark an X under grapes and an X under pears. You couldn't draw any more rows with 2 X's without duplicating some of the existing rows, right? So this is a good way of kind of making sure that you're not writing down apples and bananas, and then also somewhere along the line you're marking bananas and apples, which would be the same combination, right? So once you filled in your combination for one row, nothing else can go there. Even if there's an empty space, know that you're done, because you've got 2 combinations in one row, you're done. Move to the next row. How many combinations can you have? Or what kinds of combinations can you have? Apples and grapes. You're done with that. Move to the next row. Okay, and so this is just a a good way of making sure that you don't repeat any combinations. While you're taking your test, you'll be provided with a marker and a wipe-off board. Use the marker and the wipe-off board provided to make a tree diagram. Like we saw earlier in the example of the coin tosses, that was a tree diagram. I'm just trying to go back to the tree diagram. It's called a tree diagram because it keeps branching, right? Sometimes you'll see more branches. There's an example with that coming up. So this would be a tree diagram, just in case the test mentions draw a tree diagram, know what that means. In this portion of the lesson, we're going to be looking at combinations with more than one. So sometimes you may be asked to count the possible combinations with more than one type of item. And so just know that essentially follow the same fundamental principles that we saw with one item, except that you would be multiplying based on the number, based on the different types of items that you're working with. So in this example, Sarah is deciding what to wear. She has 3 shirts, 2 pairs of pants, and 2 pairs of shoes. How many possible outfits does she have if an outfit is 1 shirt, 1 pair of pants, and 1 pair of shoes? So again, back to what I was trying to say earlier, in this particular example, we're looking at 3 different types of items, right? We're looking at a shirt, a pair of pants, and a pair of shoes. In our previous example, we were only looking at one type, which is fruits, right? Different kinds of fruit, but one item type, right? Or one, like if you're in the grocery store, for example, there's a section with just fruits, right? This example, we're looking at more than one type, right? So if you wanted to buy a shirt, you would go to the shirt section, and then you would have to go to the pants section and the shoes section because there are 3 different types, right? So just keep that in mind because it'll matter in terms of how you approach the question. So this question, this is just telling you essentially the same thing that I just went over. This question differs from the question about Pablo, because in that question, Pablo was choosing from one overall group. So he was in the fruits section, and he was choosing different kinds of fruits. Here, Sarah is choosing 1 out of 3 groups, okay? Shirts, pants, and shoes. If you're given more than one type of item and you have to choose one of each type, you can use a tree diagram to figure out all the possible combinations. So you would just start by writing down, okay, he's got 3 shirts, so shirt 1, shirt 2, and shirt 3. And for shirt 1, after he's put on his first shirt, he only has 2 pants, right? So he can choose either pant 1 or pant or the second pants, okay? And then let's say he's decided to wear the first pair of pants. Now he can only choose between 2 shoes. He only has 2 pairs of shoes, okay? He can either choose the first pair or the second pair. And then with the same shirt, if he decided to go with the second pair of pants, he can choose between either the first pair of shoes or the second pair of shoes. Okay, and then you would apply the same logic for the second shirt on your tree diagram here. So let's say, okay, I'm not wearing the first shirt. I want to go for the second shirt. Well, again, he only has 2 pair of pants that he can choose from. And let's say he went with the first pair. Once he's put on his pants, now he's got to decide which pair of shoes. Is it the first or the second? Okay, and you just follow that logic until you've exhausted all the options that are available to you. So each branch of the tree here represents a possible Combination, as we've just discussed, the number of branches on the right-hand side represents the total possible number of combinations. In this case, there are 12 possible outcomes on the right-hand side here, okay? The question was asking us, Sarah's deciding what to wear. Oh, sorry, I kept saying he. Sarah is deciding what to wear. She has 3 shirts, 2 pairs of pants, and 2 pairs of shoes. How many possible outfits does she have, right? And so we've made our tree diagram listing all the possible combinations that she can make with those 3 shirts, 2 pants, and 2 pairs of shoes. And we know that she can wear a total of 12 different outfits with the shirt, the pants, and the shoes that she has, okay? This is just telling you that you can use the fundamental counting principle if you don't want to bother with the tree diagram. And here's how that works. You know that she has 2 pairs of pants and 3 shirts. So you would just multiply 3 by 2 and for a total combination of 6, right? And then we also know that for each of those 6 options that she has 2 pairs of shoes that she could choose from, right? So you then multiply 6 by 2, or you would write down 3 times 2 times 2, which gives you 12, right? 3 times 2 is 6, 6 times 2 is 12, okay? So again, you just want to start with the number of shirts. For each shirt, we know that she has 2 pairs of pants, 3 times 2 is 6, and then she has 2 options for her shoes. So that's a total of 6 times 2, or 3 times 2 times 2, which is 12, right? So you can either draw your tree diagram, or you can just take note of the number of options that she has and multiply them together using based on this fundamental counting principle. This example is asking us to use the fundamental counting principle to solve the problem. Gordon is at a restaurant that serves a 3-course meal, an appetizer, an entree, and a dessert. There are 3 appetizers, 6 entrees, and 4 desserts for him to choose from. Gordon will order one of each. He's decided that he's going to order one of each. How many different meals could he order if he wanted one of each, right? So you would want to multiply 3 appetizers by 6 entrees by 4 desserts, right? 3 times 6 is 18, and 18 times 4 is 72. So there are a total of 72 possible ways that Gordon could order his meal, okay? That's it for today. So I will see you next week. Have a good